Hi everyone! Today we're going to start chapter 7, and this chapter is all about solutions and colloids, although we're mostly going to focus on solutions. Solutions are homogeneous mixtures of two or more substances in which the components are present as atoms, molecules, or ions. So this goes back to the very beginning of the quarter when we were discussing types of mixtures. So solutions in particular are homogeneous mixtures. So in a solution, particles are too small to reflect light. So solutions are transparent or clear. Particles are also in constant motion. So they're not just sitting still, they're actually moving around. Also, particles are not settled by the influence of gravity. So in a solution, we shouldn't see any particles sinking to the bottom. That would describe a different kind of solution, which we'll talk about in a minute. Now, some solutions do have color to them. So on the right-hand side at the top, we can see a colorless solution, and everything is thoroughly mixed, so that's a homogeneous mixture. And then in the bottom figure, we have a solution that is blue, but everything still is mixed, and we can still see through the solution, even though it has a color to it. All right, so let's define a couple of different terms regarding solutions: solvent and solute. So the solvent of a solution is the substance present in the largest amount in the solution. So this is typically going to be water, or H2O. There are other examples of solvents, but most often we use water. So another way to think of a solvent is something that dissolves a particle. And then a solute of a solution is any substance present in an amount less than that of the solvent. A solution may contain more than one solute. So down below we have an example of a solute. So we've got a blue powder there. This is probably something that contains copper. Copper tends to have a bluish color, at least in one of its forms. And then next to that is a solvent, which is most likely water. And then when we mix the two together, so we're adding them together, we get our solution. So another example is, for instance, right now I'm drinking some coffee. So there's already dissolved coffee in the water. But additionally, if I add sugar to that water, that would be another solute that I'm adding to a solvent, and we're making a solution. All right, so there are different physical states of solutions. Typically, we think of solutions as liquids, but you can have solutions that are gases, for instance, or other states. So the physical state of a solution, solid, liquid, or gas, is usually the same as the physical state of the solvent. So I mentioned that we can have different types of solvents. We don't just use water. We could also use, for instance, nitrogen gas as a solvent. We could use oxygen gas as a solvent. And maybe we mix in some oxygen gas or some water or moisture. So if we look at air, for instance, air is composed of nitrogen gas, oxygen gas, and a few other gases as well. But the gas that's present in the largest amount is nitrogen. So nitrogen would be the solvent, and all of the other gases would be considered solutes. If we look at the top, Let's say we're making carbonated water or a carbonated beverage. The water is our solvent. It should be present in the largest amount. And then we're adding some carbon dioxide gas in order to carbonate the water. So the carbon dioxide gas would be the solute. All right. So previously we've talked about solubility. So the solubility of a solute, so remember the thing that we're mixing in, is the maximum amount of the solute that can be dissolved in a specific amount of solvent under specific conditions of temperature and pressure. So typically we're going to talk about solubility in terms of grams of solute that dissolve for every 100 grams of water. So for instance, let's say we are making pasta and we're boiling some water and we add salt to the water. Some cooks do that. If we look at the chart on the left, sodium chloride or table salt has a specific solubility. So only a certain amount of grams of sodium chloride will dissolve for every 100 grams of water. And if we look at about room temperature, which is on the x-axis, that's about 25 degrees Celsius, and we kind of go up here, that's how much sodium chloride will dissolve for every 100 grams of water, or milliliters of water, if we're assuming a density of 1 gram per milliliter. So let's extrapolate that over. So it looks like we can dissolve about 37 grams of sodium chloride for every 100 grams of water. All right, now back to our chart on the right-hand side, or our table. Let's say that we are looking at a particle or a solute that has a solubility of less than 0.1 grams for every 100 grams of water. We would consider that insoluble because it really isn't dissolving very well. But if, let's say, 0.1 to 1 grams of solute dissolve, then we would say that's slightly soluble. If we have 1 to 10 grams that dissolve for every 100 grams, we say that it's soluble. And then if we have greater than 10 grams for every 100 grams, that's very soluble. So if we go back to our sodium chloride example, we said that about 37 grams of sodium chloride dissolve for every 100 grams of water. So we would say that that is very soluble. Now, additionally, solubility is temperature dependent. So if we look at glycine, which is an amino acid, so if you've taken biology, amino acids make up proteins in our bodies. And you'll notice that this line is increasing significantly with temperature. So glycine is going to dissolve better at higher temperatures, or more glycine can dissolve at higher temperatures. So solubility does depend on temperatures. And this makes sense too if we think about sugar and tea. So let's say that you're making some iced tea and it's cold and you add some sugar to it. It's really hard to dissolve sugar in iced tea. But if the tea is hot, it's really easy to dissolve sugar. So again, that's a temperature dependence. Sugar dissolves better at higher temperatures, or more sugar dissolves at higher temperatures. All right, so again, just a quick review of soluble versus insoluble. Oh, there's a typo there. You can ignore that A there. So a soluble substance, this is a term used to describe a substance that dissolves to a significant extent in a solvent without stating how much actually will dissolve. And then an insoluble substance, this is a term used to describe a substance that does not dissolve to a significant extent in a solvent. Now, down below we have a figure showing that sugar is dissolving in water. However, sugar does have limited solubility in water, so do other particles. So for instance, if we add 1 gram of sugar to our tea, and it's hot tea, let's say, it should dissolve really well. But if we add 300 grams of sugar to our tea, most likely we're going to have some sugar that just can't dissolve because we've hit our solubility limit. So you might end up seeing some sugar settle at the bottom of our tea. I've actually seen this happen with some Starbucks beverages that I've gotten in the past where, maybe I got a fancy Starbucks drink where they add a lot of different syrups and sugar. And when you're done drinking that, there's always stuff at the bottom of the cup. And that's because you've hit your solubility limit. But also your beverage is cooling down over time, and so things are settling out of solution because remember, solubility is temperature dependent as well. However, they probably do add too much syrup and sugar to some of those drinks. All right. Now, another term we can use to describe solutions or solvents, or solutes in solution are immiscible. So immiscible is a term used to describe liquids that are insoluble in each other. So that means that the liquids don't mix together to form a solution. So a really famous example is oil and water. Oil and water do not mix with each other, so they are immiscible. So if we look at our figures down below, in the first example, we're adding 10 drops of oil to a beaker of water, and that oil is not going to mix. It's just going to settle on the top of that water. So those are immiscible liquids. However, if we add 10 drops of alcohol to our beaker of water, that will mix. So those are able to mix. And let's see. And then down below, it's just showing, you can add more and it should mix as well. All right, so let's talk about degrees of saturation. This is another way we can describe a solution. So we have 3 different terms here: saturated, supersaturated, and unsaturated. So a saturated solution is a solution that contains the maximum amount possible of dissolved solute. So off to the right-hand side, we have a picture of a test tube, and it's reached its solubility limit. So that means that the solute that's being added has completely dissolved, and we can't dissolve any more solute. We've hit our limit there. Now, a supersaturated solution is an unstable solution that contains an amount of solute greater than the solute solubility. So off to the right, you can see that in the second test tube, in the middle there are extra solute particles in the water, and this makes that solution unstable, and crystals will start to form. And then, or crystals of the solute will start to form. And then an unsaturated solution is one that contains an amount of solute less than the amount required to form a saturated solution. So in the saturated solution example, we had added the maximum amount of solute that could dissolve, but in an unsaturated solution, we haven't hit that maximum point yet. So we could still dissolve more. So for example, let's say that you are boiling water again to make pasta and you add some salt. Usually you only add a little bit of salt, right? So that means you could add more salt because more could dissolve. So that would be an unsaturated solution. Now, let's talk about some solute solubilities at 0 degrees Celsius, so at the freezing point of water. So you'll notice that at the freezing point of water, we have some solubility values listed for different molecules. And let's see if we can find some. Oh, so sodium chloride is kind of towards the middle here. So that's our table salt. And earlier we said that at 25 degrees Celsius, the solubility of sodium chloride was around 37 grams per 100 grams. And at the freezing point of water, it's 35.7. So pretty close to what we said before. Let's see, ammonium nitrate. Ammonium nitrate has a solubility of 118.3 grams for every 100 grams. And this is the compound that's found in ice packs. So that actually has a very high solubility in water at 0 degrees Celsius compared to sodium chloride. And then if we look at a liquid, so ethyl alcohol, so actually let me just put little labels. So sodium chloride is a solid, ammonium nitrate is a solid, and then ethyl alcohol is a liquid, and that has infinite solubility in water. Now, another compound that has infinite solubility is ethylene glycol, which is antifreeze. So this is what you would add to, for instance, your gas tank if you want to prevent it from freezing in the winter. And ethylene glycol is actually dangerous to have kind of sitting out because it tastes really sweet. So pets or other animals or even kids sometimes will be drawn to ethylene glycol because it does taste really sweet. So you always want to be careful leaving that out. And then sucrose, table sugar, is at the very bottom. And this is a solid and it has a specific solubility in water. And sucrose's solubility is much greater than ammonium nitrate and sodium chloride. So it has a solubility of 179.2. And of course, there's other examples here as well. All right, so again, remember that earlier we said that solubility of a solute will increase with temperature. So this graph shows a wider range of molecules, and on the y-axis is solubility, and on the x-axis is temperature. So notice that most of these solutes increase in solubility with temperature. So sucrose in particular increases significantly in terms of solubility with temperature. Potassium nitrate is another example. Its solubility increases drastically with temperature. But then notice that some of these compounds stay relatively the same in terms of solubility. So sodium bromide, potassium chloride, their solubilities don't increase to a significant extent with temperature. Now, what about down below? We have SO2 gas. Its solubility actually decreases with temperature. So remember, gases are very energetic, and their energy is proportional to temperature. So if a gas increases in temperature, its energy also increases. So you can imagine it's going to be really difficult to add a gas to, for instance, water at higher temperatures. The gas naturally wants to escape. So for instance, if you have a carbonated beverage at high temperature, remember gases have thermal expansion, right? So if you leave a carbonated beverage like a soda can in your car and your car gets really hot, the can will explode. So gases naturally want to escape a warm situation because they have a lot of energy. However, if we cool down a carbonated beverage, the carbonation will last longer. All right, so let's talk about how solutes actually dissolve in solution. So the solution process involves interactions between solvent molecules and the particles of solute. And down below is an example of the solution process for an ionic solute in water. And we've seen examples of this before. So let's say we have sodium chloride as our ionic compound that's dissolving in water. We know that in water, sodium chloride breaks apart into sodium ions and chloride ions. And remember, if we write the states, sodium chloride is a solid, sodium ions will be aqueous, and chloride ions are aqueous. And remember that water is a polar molecule. So water actually has a negative side and a positive side, and water molecules will orient themselves so that the positive ends are attracted to or pointing towards the negative ions. And then the negative side of water will be pointing towards the positive ions. Eventually, enough water will surround an ion to pull it away from its crystal lattice, and we end up with these hydrated ions in solution. Now, what if we just have a molecule that isn't an ion, but it is polar? So remember, like dissolves like. So if we have a polar solvent like water, it's going to dissolve a polar molecule. So down below, we have our solute where one end is negative and one end is positive. And you'll notice that the negative side of the molecule is always facing a positive side of another molecule. So we talked previously about how polar molecules will orient themselves that way. So water is going to do a similar thing here. The positive side of a water molecule will be attracted to the negative side of our solute, and then the negative side of water will be attracted to the positive side of our solute. And eventually water will surround each of these different molecules and pull them away from the original structure. All right, now a solute will not dissolve in a solvent if the forces between solute particles are too strong to be overcome by interactions with solvent particles. So an example of that is, you might remember that silver chloride is insoluble in water. And that's because the silver ion and the chloride ion are so attracted to each other that water cannot break it apart. But a solute will also not dissolve in a solvent if the solvent particles are more strongly attracted to each other than to the solute particles. And that's partly why oil and water don't mix. Water is more attracted to itself than it is to oil, and vice versa. Oil is more attracted to itself than to water. So again, a good rule of thumb for solubility is like dissolves like. So polar solvents dissolve polar or ionic solutes, and then nonpolar solvents will dissolve nonpolar or non-ionic solutes. So again, some of this is review. We've seen some of this information before. And then down below I have a familiar figure of sugar being added to water. So sugar is a polar molecule, so water does dissolve sugar really well. And we end up with our homogeneous solution of sugar water. All right, and then on this last slide here for today, again, just a refresher on solubilities of ionic compounds in water. So remember that group 1A metal ions and the ammonium ion are always soluble in water. Nitrates are always soluble, acetates are always soluble. Chlorates are soluble unless paired with silver, lead, or mercury. Sulfates are soluble unless paired with barium, strontium, lead, or mercury. And then at the bottom we have our insoluble ions, such as the carbonates and phosphates. However, those are soluble if they're paired with group 1A metal ions or the ammonium ion. So we'll stop there today. This was just sort of an introduction to solutions. So remember some of those key phrases, solute versus solvent. We also said that some liquids are immiscible or they're not able to mix, so like oil and water. Additionally, we talked about, here, let's go back. We talked about saturated versus supersaturated versus unsaturated solutions. So these are all terms we're going to use throughout this chapter, so just keep these in mind as we go ahead. So I will see you in the next video.